My name is Sami Benjou, and it's my pleasure to introduce you Mikko Kurimo. So Mikko, I met Mikko about 8 years ago, I think. He was with me at the IDIAP Research Institute in Switzerland, I think doing a postdoc. I was also doing a postdoc at that time. And then he went to Helsinki, and I think he's been there for the last 8 years, and he's now visiting SRI for a couple of weeks. So, well, Mikko.
Thanks, Sami, for the introduction, and it's nice to be here and to have so many audience. So my topic today will be speech recognition and retrieval using unsupervised subword language models. And the content of my talk today is I first give a short introduction where I'm coming from, what's the group, and what kind of speech recognition system we have. It's kind of the backbone of the whole thing. And then I explain the subword language models and speech retrieval thing. And at the last point is I advertise a little bit our Morpho Challenge competition that we have been running for a couple of years. So here is where I'm coming from. It's about here. So it's sort of far away from here. At Helsinki University of Technology, which is abbreviated as TKK, we have this research center called Adaptive Informatics Research Center, which is divided into 5 groups, big groups. And I'm the head of this multimodal interfaces group, which is about 20 researchers. And inside that group, we have the speech group, which is about 10 people, which are listed here. And so, of course, I haven't done this whole thing myself. It's mostly work by my colleagues and students here. And also to Matthias Kreutz, who was a previous student of mine who has also visited SRI. And I don't know, maybe not Google, but he was here about 2 years ago. So what is our research topics? We are specialized in continuous speech and unlimited vocabulary. And what we try to do is we try to develop efficient acoustic and language models for that. And the target applications are dictation, audio indexing, and speech translation. And here is our web page. So next I will explain a little bit about our system, because I think that's important to understand when you think about these language modeling units. So the basic system is quite standard. You have feature extraction first, then you have some acoustic models, which are also fairly standard. Then we have our own decoder, which is one-pass decoder especially for long n-gram language models using crossword triphones. And in the construction, we have tried to be as language independent as possible so that we can just plug in any language where we have trained the models and it would work fine. So far, we have tried Finnish and Estonian, Turkish and English. Then the language models, since we are targeting the open vocabulary recognition, we don't have any fixed lexicon. We just have a lexicon of subword units, which we can use for building any words. And because the subword units are shorter than word units, then we need often long n-grams. And then we have developed our own toolkit for growing the variable length n-grams. I will talk about that more later. And here are more about the target applications. So it's not only dictation, but also indexing large audio and video archives. For example, what's coming out from Finnish TV or other languages. And then also some multimodal interfaces things are interesting. And speech of different languages mixed together. And then we have a little demo in the web that you can try. Basic idea is that you speak there in Finnish and you get the transcription out by email. well, we could plug in the other language systems as well. But actually, Finnish is quite interesting because even if you don't understand any Finnish, you can just read the text, like pronounce every letter as it were a phoneme, and it probably recognizes you quite nice. Maybe 50% error rate or something like that, but you could see the system working. Then we have also a little translation demo, which is basically more just for fun. But the idea is exactly the same interface, but instead of getting only the text back, you will get the translation in English and also the audio in English. Okay, then for the main topic today is this subword language models. So why are we doing this? This is what we call vocabulary problem here. You can see here are a few languages. If you increase the size of your corpus, this is for thousands of words, and then this axle is the amount of unique word forms that you will find in your corpus. So you will see that Finnish is among the worst ones. But it seems to be, even every time you get new documents, you get new words as well, which is a bit difficult if you want to have a fixed lexicon. Then there are other languages like Turkish, which is morphologically quite similar, where you also add things and make long words. Arabic, and then in this comparison, English is the lowest, especially spontaneous English. But of course, English has many other difficulties for recognition, as you know. But actually, this problem is not only for speech recognition. It's, as you know, it's also for information retrieval, machine translation, all the applications where you need to have some lexicon. And then if you take languages that have a lot of words, then you are in problems. So these Estonian, Finnish, Turkish, and also Hungarian, they are known as agglutinative languages. I have an example here. What is the agglutinative morphology? So it means that you keep on adding things after each other, and then you get very long words. Like this one is kahvinjuojallekin. It's not even a rare one, it's quite common. The idea is that it's almost like a sentence if you translate it into English. Or this nykyratkaisuistamme from our current solution. So it's just several words that are just stuck into one. So there are prefixes, suffixes, and also compound words. So when you think about making a lexicon of some subword units, then here are a few questions that I thought that might characterize the problem. So what you need to do is you need to find that kind of units that you can use for predicting what's coming next. So they need to have some meaning in them, the units. And then in speech recognition, you also need to be able to define the pronunciation for each unit. So you can't arbitrarily split, let's say, English words. For Finnish you could, but for English not. And then what is often the case, for example, in audio indexing, you will have a lot of different stuff there, also from other languages. Well, again, if you think about Finnish, then we often use words that are the same as some other, like we are just borrowing them from English or other languages. So if your system is completely customized for one language, then you just don't know what to do with the foreign words, or you just forget them or something, which is not good if you think that they might be the most important words. And then again, in speech recognition, it's important that if you are recognizing the subwords, then your recognizer gives out just a kind of continuous flow of subwords. But that's maybe not what you want to do. If you want to dictate something, then you want to have the kind of the real output. So you need to glue them back into words so that they look nice. So you need also to do that. And then when you have developed system for one language, of course, you won't like to try it in some other language, so the system should be easily portable to other languages. And here is one slide motivating our approach, what we took. So if you think about automatic understanding and production of a language, then you need to know or understand something about the inner structure so that you can produce words. So our approach is that we took unsupervised learning. We didn't want to be developing any rule-based systems. So the idea is to find the optimal segmentation of each source text into morphs. Those are the subwords units, kind of morphemes. We call them morphs because they are statistically defined. And we define some cost function and try to minimize that cost function. I won't talk much about this. I just explain the toolkit, what we have. You can try it. There is a demo also in the web. You can type in any word and you will see how it's split in the subwords. So this is fully data-driven, unsupervised machine learning algorithm. The idea is that you have a lot of text data in the language and then you just go through the data and see that what kind of phoneme strings or letter strings often appear there and make a deduction that that might be a good subword unit. So the result is surprisingly that it will look quite much like the linguistic morphemes, which is kind of a nice thing, we think so. And it's language independent, so there are no morphological rules or annotated data needed. Here is the code available, and it also includes programs to segment and align all possible words, what you give them. Then if you think about speech recognition, then this is only one step, is how to split the words into units, and then you need to develop the language models. And as you know that if you have very large language models like the state-of-art systems, they often have gigabytes of language models. They are kind of a bit bottleneck in many things that you want to do. Either you want to teach them or use them or just analyze them because they are very big, even for big computers, not to mention small ones. If you wanted to have your recognizer in a mobile phone or something, then you didn't want to have a large language model. And also, in large language model, there's typically many rare words. And because you are estimating the probability based on your training data, you don't have good estimates for the rare words. So it's one difficult thing. Of course, you could build compact language models by first training a big language model and then starting to prune it, taking out things that are not so important. Of course, in principle, it's good. Okay, it's probably might even be better than our approach, but in practice, it's difficult because then you would need to first collect the statistics and then train the huge model. So our approach was to grow the n-gram context from unigrams, starting from unigrams, like this example. If you have a unigram like recognition, then you would like to grow it. You think that what words before it would increase the information content, so you maybe see speech recognition, character recognition, they are common things. Then maybe large vocabulary speech recognition is common. So you build your model by adding these kind of pieces. And this is our toolkit that it's also public domain in our webpage. So it's a bit similar like a SRI language modeling toolkit that I suppose almost everybody is using nowadays for training n-grams, except that this has this ability to grow the language models from the short ones, so you don't need to collect huge statistics and make the big models first. And also we have applied this Kneser-Ney smoothing, which is the state-of-art smoothing algorithm, and it's not so straightforward how to do it for growing models because you need to keep track on all the statistics that affect to the smoothing. But now we have the toolkit, and what we get out of it is a compact set of properly smooth variable order n-grams. There is one example in English. You will see that if you are splitting the words into morphemes, this is kind of end of word tag here, you quickly come into long n-grams. And here the cost function is the kind of how many n-grams you will have in the model and what is their probability. And the whole system now, we have talked about these two pieces, the Morfessor algorithm and then this VariKN algorithm, is that they are actually, well, they are built for our speech recognizer, so the beginning idea was that they would be compatible with each other. But of course, you could use other language models and other units as well to build a system. And about the performance, what we have tried so far, we have tried in language modeling for speech recognition, then some information retrieval, spoken document retrieval, and machine translation tasks in several languages: Finnish, Estonian, Turkish, English, German, Egyptian, Arabic, Hungarian. And we have been told from other people that they have tried other languages as well, so the list is growing all the time. And then we have organized these competitions that I mentioned, where this Morfessor and VariKN models have been used as a reference to compare what the participants get, and also to give them first to try the system, because they are public domain, so they can download it and try to solve the system, try to solve the task with our system first, and then see if they can make it better. Here are some error rates. Sorry that this slide is half finished, but maybe you can understand. So these are different automatic speech recognition tasks for different languages. Here is Finnish, Estonian, and Turkish, and here is the word error rate. The yellow bar here is the morph-based approach that we are suggesting, and this is the word-based approach, the bluish bar here. The idea in this slide is to show that what we see is almost like a constant improvement in different settings, so different languages. And this doesn't mean that Finnish is easier than Estonian, but it's just that we had different tasks. The Finnish task was speaker dependent, read speech, it's like broadcast news type thing, and then Estonian was a telephone speech with 1,000 speakers, so it's more difficult task, you get higher error rate. But the improvement seems to be almost constant, and it's quite significant if you know about speech error, word error rate. Then about using this subword units in speech retrieval. So how does it work in practice? Well, you have the transcripts of the speech, and you just split the transcripts and the queries, what you have, into morphemes. And then you do the matching in the morpheme level, not in the word level. And this is especially nice for recognizers like ours that already produces subwords. So you don't even need to do the splitting because the recognizer gives it out. This is quite important for speech retrieval because there are some rare words that are difficult to recognize that often are the most interesting. For example, names of people or some foreign words or something like that you can't recognize by your speech recognizer, you fail always. But if you split them in some way into subwords, you may be able to, maybe not to recognize all the subwords, but at least some of it. So you might be able to index the word correctly. And another thing is that once you have the subword-based recognizer, you don't need to do any stemming or other word post-processing for the indexing, because you already have the kind of ideal units coming out from the recognizer. So you kind of avoid this possible source of errors. And actually what we have found how to achieve the best performance is to add both of these two. So you do the normal word-based recognition, word-based indexing, and then you do the subword-based recognition and indexing, and then you add both indexes. This is kind of straightforward thing to do in indexing. So you have two indexes and use them both. So some words that are easier to recognize by word-based recognizer, then you use the other links, and then some words that are not be able to recognize, then you use the other. And this seems to give very good results. Of course, you don't avoid all the speech recognition errors, but quite many of them. And then with a subword-based index, you can do all the usual tricks that you have done with word-based indexing, latent semantic indexing, query expansion, document expansion, and using lattices and n-best lists. Here is just one example of how to use a confusion network for indexing. So this is one word which is recognized as subword units. So first this word symbol, then valtio, which is a state in Finnish, and then this is skip, another skip, and then this other inflective suffix of the word. So the first best result is this one, and then the correct result is something different. So if you would just index the first best based on the first best result, then you would miss the word. But if you are indexing based on the whole confusion network with these probabilities, you might get the correct word as well indexed. And the last thing what I wanted to show here is this Morpho challenge competition that we have been having for a couple of years now. So the idea here was that we give this task, advertise it, and then try to get other people to participate, and then we evaluate and compare who would have the best algorithm. So we had two competitions, one starting from 2005 and one from 2007. 2005 was kind of the simplest form, just implement unsupervised algorithm that segments all the words in the corpus. We evaluated it based on the linguistic gold standard morphemes and then statistical language modeling and speech recognition. Then the second task that we had last year was a bit more complicated. So not only split the words, but find the morphemes, meaning that some of the splits might have the same meaning, or they would be some kind of allomorph forms of the same morpheme. So you would also need to do some clustering there. And then we evaluated it by information retrieval also. So the motivation was not only to test our own algorithm, but test also other people's algorithm and see what kind of algorithms work the best for each application. And then also we wanted to find out what would be the good lexicon units for different applications like machine translation, speech recognition, information retrieval. And one aspect that was important from the beginning was that discover approaches that would be suitable for a wide range of languages, not only for English or something that everybody works on. So this was the first challenge. So the challenges are organized by this Pascal Network of Excellence, which has been now running 5 years in European Union, which gives us some funding. But it's, of course, participation is open to everybody and free of charge, and actually most of the participants nowadays are outside from Europe, from the US. So in this we had two evaluations, what we call two competitions. First was to compare the morphemes that the participants gave to linguistic morphemes and using F-measure, measure that which are the closest one. Maybe this is not relevant for applications, but it's interesting in the linguistic point of view, and maybe give some explanation about the behavior of the algorithms. And the other competition was testing speech recognition experiments where the language models were trained using the units that the participants submitted. Here are the linguistic results. So the F-measure means that the higher the percentage here, the closer it is to the linguistic morphemes. And we see here that these two are our own baseline algorithms, and these are the participants' algorithms. So that actually about half of the participants got quite nice algorithms that were close to ours, and then the other half not so good algorithms. So the different colors here are different participants' results. And then we use the same things in language modeling, trained language models and in different languages. So the lexicon size was not fixed here. So of course it depends on the participant, what kind of subwords units they are proposing. Some are proposing shorter units, which are not so many of them, and then some are proposing longer units that you have a larger lexicon. So we let it be free. Luckily, our tools were able to handle even 1 million words of lexicon if necessary. Only thing what we fixed was the size of the language model, so that it should be something like 10 million n-grams for each language, so that it would be fair for the different algorithms, the same amount of free parameters. And then the speech recognition evaluation, we did the Finnish evaluation by ourselves, and then our Turkish partners did the evaluation of Turkish recognition. And this is also two different systems, because our system was completely homemade, which was quite good, but the task was quite easy. And then the Turkish system was kind of using the standard HDK and AT&T language modeling tools. And they tried to make a fast system that would be running almost real time. So error rate was higher. So here are the results for Finnish. These are again the different participants, and now that's an opposite. The more errors you make, the worse system you have. So here were our baseline algorithms, the Morfessor ones. And you see that some of the participants still are quite close to it. So it seems to be quite robust that if you have kind of meaningful subword units, and with our language model toolkit, you can get good language models. But not all of the participants would be able to do this. Okay, the full report is here. You can still find the web page it's running, and you can even try the tasks. The data is still there, and we can evaluate if you want. Just send us email and we will do it. And then it's proceedings. Okay, and this was the latest thing last year, the Morpho Challenge 2007. This was again part of the Pascal network, but we also get help from the CLEF, which is another center of excellence in EU. It's kind of corresponding the TREC here in US. So this CLEF means Cross-Lingual Evaluation Forum for Information Retrieval. So why we joined the CLEF as well was that they have a lot of the information retrieval evaluation tasks and data. So we didn't have to collect them ourselves. And again, participation was open to all and free. And here the rules were a bit similar. So again, you only need to, we gave out a list of words, and you need to supply the subword units or the splitting of each word into subwords. And then we would evaluate it, comparing to the linguistic morphemes, and then do the information retrieval experiments using the subwords units as index terms. Training data was here for different languages. And then we also gave out some gold standard sample for each language to show the people what kind of stuff there is. Because we can't expect that everybody understands Finnish and Turkish. So here are some examples of different languages. What could be the morpheme analysis? So not just splitting the words, but splitting the words into some kind of morpheme classes or the morphemes. But of course, you can imagine that if you are having an unsupervised learning task, then you don't have these labels, because you just try to cluster words. So there's a problem how to evaluate this if you don't know the correct labels. So we solved this problem in a way that the participants are free to give whatever labels they want to their morphemes. We only check that those pairs of words that share the same morpheme in the gold standard, and see that if those words share any morpheme in also the participants' systems. So if those two words share the same morphemes, then we would get the point for them. But if those two words didn't share any morpheme, then we think that there is an error. So we took a point off. And of course, we computed the matches in a large random sample of word pairs where those had a common morpheme. So we can again compute the precision and recall and then the F measure. So the precision would be the proportion of the suggested word pairs that the participant is suggesting that also have a common morpheme in the gold standard. And then the recall would be the proportion of sample from the gold standard that also the participant suggested that they would share a morpheme. And here are again the results. the higher F measure, the better. And here we see that there was one participant who got significantly better results than what our baseline algorithm. It was good what we think. And then several participants got almost as good, and some. And also because the data was about the same size, and you can see here that the Finnish language had about 2 million different word types. So if you would use the full vocabulary, you would need 2 million words. But then, okay, Turkish had a bit little less data, but German that had an equal amount of data, they only had 1 million different word types. And English, it's only 400,000 different word types. If you think about watch the results a bit closer here, you see that they actually, this is for German, quite similar than for Finnish. Not the same algorithms were the best, but those algorithms that were good in Finnish, they were also good in German, and vice versa. And English as well. And now the more interesting evaluation was the information retrieval one, to see that which of those morphemes would work in practice as well. Here are the clef data that we were using, documents from newspaper articles, and then test queries, and then binary relevance assessments. So we are very thankful to Clef, because especially those relevance assessments, they are difficult to get, and it's a hard manual labor to do them for the comparison. Then we, by curiosity, we made a bit more different kinds of reference methods for the participants. So, of course, the Morfessor, two applications, two versions of Morfessor, and then we applied the dummy, which means that we just put the words there without any morphological analysis and use them as index terms. And then grammatical indexing, which is that we would use the actual gold standard segmentations that were given by the rule-based algorithm and use that. And then the Porter stemming, we could try that as well. That's what the information retrieval people usually use. And then we had one participant who suggested the hybrid method based on our baseline algorithm and some rules that were trying to improve it. And the evaluation was made by the standard Lemur Toolkit. And there was another problem, was that people are usually using some kind of stop list in information retrieval. But if you have your own units, like morphemes, then how would you define the stop list? That would be the same for everybody. So we solved this by just fixing a frequency threshold of units, that if the morpheme is more common than the frequency threshold, then it would be included in the stop list. And the frequency threshold in our tasks was something like 100,000. And it seemed to be quite robust, so if we increased it to 200,000 or decreased it to 50,000, the results were not much affected. But outside that range, it would be important. And then another thing that we didn't first think that would be important were the out-of-vocabulary words, meaning that we had different training data for training the word splitting and then the information retrieval test data. And of course, at least in some languages, there were a significant amount of words that were not in the training data. And we first thought that, oh, well, we just skip them, don't care. But then we asked the participants again that maybe they could also provide analysis for those words so that you could check that does it really make a difference. Here are the results for Finnish. You will see here that the first bar, this is again is mean average persistence, which is the kind of standard evaluation metric for information retrieval. The first bar is the one which has the out-of-vocabulary words analyzed, and the second bar is the same participant without the out-of-vocabulary words. So you see quite a difference here in Finnish. In the other languages, there were not so much difference. And you see here that the same participant that had the best results in the morphological analysis also had the best results in information retrieval. And the Morfessor baseline came second, and then some other participants were almost as good. Then you see that for Finnish, the Porter stemming and the dummy approach didn't work very well at all. German, it's kind of similar behavior here as well. Maybe the difference between using out of vocabulary words was not so big. For English you see that the Porter stemmer is the best. But actually these unsupervised systems are pretty close as well, which is kind of interesting thing that you can, without any rules, you can get almost as good approach. But also you see here, probably at Google you know this, but it's not evident for everybody that if you are just using the words as such as index terms in English, the result is not very good. So you need to do some morphological analysis or stemming or something. So here is the dummy approach. So almost all of at least the better algorithms were able to beat it. And another interesting thing still is this grammatical. So you would think that if you are using the gold standard algorithm for morphological analysis, then that should be the best morphological analysis for information retrieval as well. But as you see here, it's this one. So there were a couple of algorithms, unsupervised algorithms, that were better, and the difference is significant here. And the explanation that what we thought is that, especially for the rare words that are important, there is always a kind of problem of coverage based on this rule-based systems, so they were not able to probably model. Yeah.
So is the morphological splitting context independent? So a word is split the same way in any given context?
Yes. That's actually, it's not the optimal solution. Probably it would be better to split the words using the context. But it's kind of, it was difficult for organizing this competition. That we would then need to give the whole corpus to everybody now. It's way easier to us to just give the list of words for different reasons. But that's actually one thing that we are now changing for this 2008 competition, that we would give the whole context and then people could use that for splitting.
But you don't have the context on the query side, right? So it may actually be a good idea to do it like this.
Well, it depends on the length of the query.
And how natural language is it?
Yeah, of course it depends. If you think about these clef queries, they were usually very long and quite specific, so it's kind of good context. But if you think about queries that people are using in Google, then it's different, certainly. Okay, then conclusions. So we currently have about 10 different groups that are participating in these things. Languages are Finnish, Turkish, English, German. And then again the website where you can find the proceedings, the presentation slides from the workshop and full results and everything. And then some future directions. So for this year we are adding a new language. It's probably either Hungarian or Arabic, depends on how we get the data. And then we have been thinking about some new tasks as well, in addition to speech recognition and information retrieval. So maybe question answering type of thing, or machine translation, or some word alignment, which is a kind of smaller problem inside the machine translation. Then where to have our next workshop. Maybe we could get some new supporters, so that would be interesting. And then, of course, to get some new and improved learning algorithms from the participants. Yep, that concludes my talk.
Questions? So English morphology is weird, I guess, and there are lots of times where you don't just break words into subword units. For example, if a word ends in Y, if a noun ends in Y, you form the plural usually by adding IES. Does your system, is it able to take that into account and say that this isn't actually a concatenation of subword units, but there are certain things that happen at the boundaries of those units, for example?
No, our system is actually quite simple. So it only understands kind of prefixes, stems, and suffixes. And then, but actually it seems that the simplicity is kind of a good thing, because then in some other ways it can cover those things. So if some words have different stems, a couple of different stems, then the system will find the stems and maybe cluster them together, and here we are. Or if they have some inflections, for example, like this plural thing in English, there would be several different plurals, but the system could probably find them.
Other questions? Better use this.
So I actually have two questions. So first one would be, so you're now assigning probabilities to strings of morphemes as opposed to words. So that means that you may start generating things that are actually not legitimate words, right? Your morphotactics are too relaxed there. So how do you ensure that you actually get correct word sequences out of the recognizer to measure the word error rate and everything?
We don't.
Oh, you do?
But in practice, that's not a problem, I think. Yeah, and also, if you have the language models, n-grams, then the n-gram probabilities would be higher for those subwords that make the full word, kind of the normal words, or at least common words. But it can be like in Finnish that you can just connect subwords, get a new word that is not in your dictionary, but it's still a correct word, but nobody just uses it.
I see. So this is a good thing for Finnish, but I don't know if it would be a good thing for English.
Yeah.
So another thing is, do you know what the incidence rate of this morpho splitting is if you take running text?
So what rate?
So for example, if you take running text in English or Finnish or German, and then you run your morphological analyzer on it, how many words in the original text actually get split? Because I would expect they're very different.
Yeah, that's actually, we haven't computed that. At least I don't remember it, but as the system is kind of statistical, it often thinks that common words that have morphemes, it's not worth splitting them because the words as whole as are common and appear in different connections. So I'm not sure if it's good or bad thing. At least in speech recognition, sometimes it's good to have long units for the acoustic modeling, so that they are not so confusing to each other. But it seems to be that it's maybe also for information retrieval can be. In some cases, they might have a bit different meaning, the words in different forms. I don't know. For very common things.
Do we have other questions?
Sort of a comment on what he had said, leading into a question. So, in analysis of actual human speech, in any language you want to pick, what you would consider perhaps the error rate, what's actually said, not interpretation, not the computer side, but like the speech production itself has probabilistic error rate attached to it, and this is how, like, over large periods of time, you see unification of languages and evolution of new words and shift in pronunciation and whatnot. So it's not really accurate to say that the underlying language which you're modeling has strict boundaries, because it's not just evolving, but the actual individual speaker is making regular errors. Now, towards that end, the error rate for a particular individual speaker is very dynamic. It's something that's going to be a function of some constant error rate that they experience, plus their stress in their current environment, their level of distraction, and having some kind of model of the underlying rate at which a particular speaker is making those errors would perhaps give you a better tuning parameter for deciding what they're actually trying to say, which is something in practice that actual human listeners do. We try to sort of model how frequently someone is misspeaking and broaden our search for what they're saying, and spend some more time on that. And if someone's making a lot of frequent errors, we start dropping the probability that they're using improbable words. We start focusing on the much smaller set of probable words, but doing a lot more searching in that space. And so in that regard, have you looked in that direction for ways of possibly dynamically tuning how you do the morphological search based on what seems to be the error rate that you're encountering?
Yeah, that's a good point. Yeah, we haven't really considered that, but I think it could have some importance. But of course, it's also different. And here we have been mostly dealing with planned speech or read speech or something. But when we turn into spontaneous speech, then those errors start to appear.
Question?
So you said that your speech recognition system is based on crossword triphones. I was wondering if you've had the idea or done the experiment to use your subword units that you've learned and make a sort of a whole word model, except using those subword units. So basically trying to learn the pronunciation or the sound of each piece of those subword units to try to model the context that's happening within those units. Does that make sense?
Yeah, well, we haven't tried that. I'm not sure if it's a good idea, because there are still kind of tens of thousands of those units. And yeah, I don't know.
Any other questions?
Did you have a sense of the decoding speed changes between using word units and subword units, and the fact that you have to use longer context and stuff like this in practice? Is it really changing your
So you mean
ASR decoding
speed of the
performance?
speech recognizer?
Right.
No, it's, well, we are not really real time. So it's maybe 2-3 times real time. So it doesn't make a difference. But often with those long n-grams, you can actually forget the past quite quickly. You will see that the best hypothesis will only differ to the last 3 subwords or words, and the rest will be quickly fixed. So it doesn't really seem to cause any delays.
No more questions? Okay, so let's thank the speaker again.